Okay, let's turn to the problem set on the central limit theory. Now you can see I have opened several applications like a whiteboard in Excel because we probably need both. But let's get started with a simple question. So the central limit theorem states that as the sample size increases, the distributions of the sample means approach the normal distribution. So that is about the sampling distributions of the means. There's actually a good chance that the sample medians would also decrease. But yeah, we were talking about the distributions of the sampling means. Consider two populations distributions labeled A and B. Distribution A is highly skewed and non-normal, while the distribution B is slightly skewed and near normal. In order for the sampling distributions of A and B to achieve the same degree of normality, then population A will require a larger sample size. As the sample size blank, the variation of the sampling distribution of X, the mean of the sample, there's the sample size, it's an inverse relationship. As the sample size increases, the variation of the sampling distribution decreases. So that is D. And of course, that has to do with the standard error. And as you know, the standard error is S. So the standard deviation of the sampling means, which is equal to the standard error, that is equal to the sample standard deviation over the square root of n. And of course, if n goes up, the standard error goes down, and the distribution, instead of looking maybe like this, if the sample size goes up, the distribution has a smaller variation around the mean. Okay, a manufacturing company measures the weight of boxes before shipping them to the customers. If the box weights have a population mean and standard deviation of 100 pounds and 16 pounds respectively. So in this case, we actually know the population mean. So let's write that down. So the population mean is 100. And the population standard deviation, sigma, is 16. So then the distribution looks like this. We know that the mean of the sampling distribution is equal to the population mean, and the standard error, now we write sigma, is equal to the population standard deviation 16 over the square root of n. But here we don't have a sampling distribution, and we just have the standard deviation. Sorry, so we just have this, which is equal to 16. Okay, so now the question is, what's the probability that the average of 1, okay, so we don't have a sample, we just have 1, averages out to 104 or more. So that means we are interested in this area. So now we calculate the z-score. We calculate the z-score because we know the population standard deviation. So we want to know how many standard deviations is a 104 away from 100. So we use the formula. We subtract from 104 the mean, and divide by the standard deviation of 16. And then we get 4 over 16, and that is 0.25. So now our critical T is it's probably 0.40. But anyhow, so what we want to do is we want to calculate the z-score. Maybe I can zoom in a little bit. Equals. So in order to find the z-score to the right of 0.25. So let me do that here. So again, what we now need is, so we have a z distribution. And we need to know the area to the right of that C of 0.25. And of course, it's the same as the area to the left of negative 0.25. So I can use the formula equals norm dot s dist, and now I just say negative 0.25, and I want it cumulatively, and then it is indeed the 0.40. And again, what I just did is, the area to the right of 0.25 is obviously the same as the area to the left of a z-score of negative 0.25. So those are the same areas. Okay, so, and again, this formula always gives you the area to the left of a z-score. So if I put 0.25, I would get 0.59. What I could also have done is just say then, okay, then I have to subtract 1 minus, because, otherwise we will have gotten this area here. If I said norm as inf 0.25, I get this area, but because I want the one to the right, then I have to do the 1 minus. Okay, so it should be clear. So now let's move to the next one. A manufacturing company measures the weight of boxes before shipping them to the customers. If the box weights have a population mean and standard deviation, okay, so we are still having the same. We know the population mean is 100, and we know that the population standard deviation sigma is 16. Then based on a sample, so now we take a sample of 64. The probability that the average weight of the boxes will exceed 104 is, okay, so now we have a sampling distribution. So we don't have the distribution of the population, but we have the sampling distribution. And the sampling distribution looks like this. We have here the z-score. And actually, no, not yet. So we don't have the z-score there yet. So what we do have here is all possible averages that you can get if you take samples of 64. But what we know is that in the sampling distribution, the mean of the sampling distribution is equal to the population mean, and the standard error or the standard deviation of those sampling means is equal to the population standard deviation over the square root of n. So now this is 16 over 8 or 2. So that is our standard error. So now we want to know what's the probability that 64 randomly selected boxes average out to 104. So we want to know what's the probability that we can get 104. And of course we can use the Z distribution because we know the population standard deviation. So now we calculate the Z-score, and the Z-score is 104 over 100, 104 minus 100 over the standard error, which is 2. So now we get 2. So that means that a 104 average from the population average of 100 is 2 standard deviations above the mean. And so now we are interested in this area here. And that is equivalent to the area to the right of a Z-score of 2. So now we can use again the formula again, equals norm as dist. But then, because the area to the right of 2 is the same as the area to the left of negative 2, I just can enter this shortcut, and then we get the probability of 0.22. Consider a sampling distribution based on n equals 3. The standard deviation of the population of all sample means is blank less than the standard deviation of the population of the individual measurements, and that's probably a sigma here. Let me just quickly fix this and turn that into a sigma. Well, and that is always the case. Why? Because the standard error of a sampling distribution from the population is equal to the population standard deviation over the square root of n. And of course, if n is greater than 3, the denominator is greater than 1, so it always must be less than the population standard deviation. So if the sample population has a mean, okay, it looks like there's some, so has a mean of, that should be a mu, actually an x bar. No, it is the mu, because the sample population has a mean. So let's put here the correct Greek letter. So if the sample population has a mean of 48 and a standard deviation of sigma equals 16, then the mean and the standard deviation of the sampling distribution of x bar for n equals 16 are. Okay, so now what we know is that the mean in the population is 48, but the mean is an unbiased estimator, so the mean of the sampling distribution is also 48. But the standard error is equal to the population standard deviation over the square root of n, and that is equal to 16 over the square root of also 16, so that is 16 over 4, so that's 4. So the correct answer is 48 and 4. Okay, last question. Whenever the population has a normal distribution, the sampling distribution of x bar is normal or near normal distribution for only large samples, for only small samples. Now in that case it's pretty normal for any sample size, because if it comes from a normal distribution, the samples are normal too. Okay, so I hope that clarified the importance of a sampling distribution, and it also concludes the chapter on the central limit theory. And it is a very important one, because building on the central limit theory, we do our inferential statistics like hypothesis tests or confidence intervals. But anyhow, let's just stop here, and then let's continue with another topic in the next lecture.